have been discussing the wave nature of matter, and what I have presented in the last couple of lectures is that a particle with momentum p has wavelength lambda associated with the waves traveling with it. That means, lambda wave is h over p. What we have not said what kind of waves these are. The only thing we know is that there is some wave traveling with the particle when it moves, and it has a wavelength h over p. And we have also discussed how to check or test for the existence of these waves. And 3 experiments that I discussed was diffraction of particles from a crystal, which is similar to diffraction of X-rays from a crystal. Both satisfy the Bragg relationship. That says 2d sin theta equals n lambda, where for X-rays it will be the wavelength of X-rays, and for electrons or the particles that are diffracted from crystal, it will be lambda of those particles, which is n h over p of the particles. I also presented to you possibility of electrons doing interference in a double slit experiment. And one more thing that I discussed was Kapitsa, Dirac scattering, which is scattering or Bragg diffraction of particles from standing waves of light. Just dwelling on this concept a little more, I want to emphasize that there are some misconceptions that should be cleared right away. Misconception 1, and that is that since there are waves associated with particles motion, the particle must be moving as a wave itself. That means, sometimes there is a misconception that the particle itself is performing a motion which is wave like with a wavelength which is lambda given by h by p. This is plain wrong. What this wave business associated with particles says is that if there is a particle which is moving with momentum p, with the particle there is a wave associated, and we do not yet know what this wave is until we write equation and start interpreting, but experimentally it is established that there is a wave associated which has a wavelength lambda which is h over p. So, this should be very clear. There is a particle moving and there is a wave associated with it. Number 2, diffraction of particles, or this is same as interference of particles, is statistical for a large number of particles. What I mean to say in this is, suppose I am doing a double slit experiment with electrons coming from this side, and finally I see an interference pattern. The misconception is that when I let these electrons go through, one electron comes and the second electron interferes with this electron, and then they interfere and go somewhere. That is a misconception. What is happening is each electron that comes somehow gets divided. It does not get divided, its wave gets divided, and it is the wave associated with each electron that forms an interference pattern. It is just that one electron can go either here or here or here or here. So, you do not really see the interference pattern, but it is being formed. So, what happens when slowly, if you let one electron come at a time and collect a lot of data, even when only one electron is allowed to pass through the slits at one time, after you collect a lot of data, you see a pattern emerging like this. And what that means is that each electron is interfering with itself. More precisely, the wave associated with each electron goes through both the slits, and when it comes out, just like light wave interference in Young's double slit experiment, these waves also interfere, and then accordingly particle goes somewhere. Particle cannot be divided. So, never think that it is only when a large number of particles come, they interfere with each other and then they form an interference pattern. No, it is the wave associated with each particle, single particle, that interferes with itself and creates a pattern. Same thing in crystal diffraction experiment also. Wave associated with each electron, each particle interferes with itself, and then when you collect a lot of data, you see the pattern emerging, that particle is going somewhere. So, I hope I have cleared these two misconceptions which are quite prevalent. Now, having done that, I also want to give some time to Dirac-Kapitza effect, in which what we said is that if I take a standing wave of light and let electrons or some particles come from this side at particular angle theta, you see a large number of electrons diffracting at exactly the same angle with the same momentum p. How does this happen? So, what happens here is, recall from our discussion on waves that a standing wave is a wave traveling this way and a wave traveling the other way with equal amplitude. So, what happens when an electron comes in? It may absorb a photon from wave coming down, and therefore, it gets a kick in certain direction, and then the wave going the other way may stimulate it to give out that photon. So, it gets another kick. Let us do it more systematically. So, when this momentum p is coming in, and suppose the electron absorbs a photon of frequency nu from this side, it gets a kick of momentum of photon, which can also be written as h over lambda light, which is h nu over c. Then, since this is a standing wave, there is a light coming this way also. It can stimulate this electron to give out the photon going in the opposite direction, and this adds another kick to the photon, which is again h nu by c, and therefore, finally, the photon momentum makes it go this way. So, it was coming at an angle theta and went out at this angle theta, keeping the p the same. How much is delta p? Delta p is this big arrow. So, delta p is in the direction of photon, which is equal to 2 p electron sine of theta, which you can see from this diagram that I have made, and this should be equal to h over lambda light times 2, because there are 2 photons that are involved, which is 2, I can write this as 2 times h cross over lambda over 2 pi, which is same as 2 h cross k light. You can write it in many different ways, but this also tells you h cross k is the momentum of light, and therefore, sin theta times p of electron I can write as 2 times h over lambda electron, which is same as 2 times h over lambda light, and that immediately gives you that lambda light times sin theta equals lambda electron, which is the same as Bragg's condition as derived in the previous lecture, with this difference between 2 planes, same planes being d, which is lambda light divided by 2. So, this is a way of understanding Dirac-Kapitza or Kapitza-Dirac effect, where the electron absorbs a photon and then it is stimulated to emit that photon in the opposite direction. So, it gets twice the kick. So, having done that, now we want to understand about this wave and the particle a little more. Now, a wave is something that is spread over space. So, if you take a plane wave, it may be spread all over space. So, I am drawing it as much as possible. So, this is a wave which is spread over space. On the other hand, if you look at a particle, it is localized somewhere. It may be here, it may be here at one position. So, this is localized at one point. If there is a wave associated with a particle, particle is localized, but the wave is spread all over the place. Where is the particle? Is it here? Is it here? Is it here? Where is it in the wave? So, question arises, where in the wave is the particle to be found? That is one question. The other question is, let us also calculate the speed of these waves. If I do a calculation in non-relativistic terms, non-relativistic, v waves is going to be the frequency times lambda. Frequency is nothing but energy E over h times lambda, which is h over p. H cancels and I get E over p, which is nothing but p square over 2m over p, which is p over 2m, which is v particle over 2. On the other hand, if I do a relativistic calculation, right, so let me do a relativistic calculation. Then I have again v wave is equal to energy, which is now going to be m c square over square root of 1 minus v square over c square times 1 over h times the momentum, which is h over momentum is mv over square root of 1 minus v square over c square. Then I cancel this term, I cancel m, I cancel h, and I get c square over v particle. In both the cases, I see that the wave speed is not the same as v particle. So, what is going on? So, two questions that have arisen out of this consideration of a wave associated with a particle. Number one is where in the wave is the particle located, and question number two is how is the speed of particle enters the wave picture, and both of these are answered by something called the group of waves, and that is what I am going to discuss next. So, when we say that there is a wave all over the place and I do not know where the particle is located, which should have been somewhere here, where I show it by the dot, red dot, what I would say is the particle is actually, when it is moving, is not represented by an infinite train of wave. Rather, this wave could be localized around the particle position. So, particle is somewhere, there is a large amplitude. So, it has a profile, the wave has a profile, and particle is to be found within this profile. So, let us say if this is delta x, the extent of this wave spreading, then particle is found to be found within this profile. Notice, by making that statement, I am actually saying much more than what I just stated. What I am saying is, if I associate a wave with a particle, it can best be located within some delta x. It cannot be located precisely, and that is a quantum mechanically true statement. I cannot locate the particle precisely with delta x being 0, because there is a wave associated. It could be anywhere within that wave. So, for example, when I take this particle and a wave associated with it, with a profile that I made earlier, it could, for example, be that the waveform, which now I will introduce this Greek symbol psi x, because I am going to use it later, is going to be of the form, for example, it could be sine of some k 0 x minus omega 0 t times, let us say, e raised to minus x square over some constant sigma square. So that as you go far away from that position of the particle, it decays. So, if the position of the particle is at x naught, I could write this as sine k naught x minus omega naught x e raised to minus x naught square over sigma square, where k naught is related to this lambda of this undulation. So, I can write this as 2 pi over lambda 0. Omega 0 is related to this energy of the particle over h cross, which is same as 2 pi nu, which is same as 2 pi e over h. So, there is some wavelength associated, but there is also a profile. So, not only k naught is present, in such cases other k's are also present. And how are they present? Again, I go back to what I told you about how to represent a general wave in terms of eigenfunctions. So, this I can write as a Fourier transform or sum over different k's times some constant a k sine of k x minus omega t. I could equally well write this as summation a k sine of omega t minus k x, depending on which way do you want to think. So, I can just change the sign and write it like this k, and in continuous case this is written as a Fourier transform, which is integral of sum a as a function of k e raised to I omega t minus k x dk, k varying from minus infinity to infinity, and a k is maximum for k equals k 0, because you see that is the predominant wave form and it decays away from this. So, for example, it could be of the form, if I were to plot a k versus k, it could be of the form, this is suppose k naught, it is largest there and then the decays. So, there are some waves being mixed, this is delta k, within some delta k. What is k related to? By de Broglie's hypothesis, k is nothing but 2 pi over lambda, which is nothing but 2 pi over h times p. This gives p over h cross, which implies that p equals h cross k. So, momentum of the particle is related to k as h cross k, and when I say that there is some spread delta k, that means momentum of the particle is not specified very precisely. A large chunk of it is k 0, but there is also a spread in it. So, not only the position is not specified exactly, even the momentum has a spread. Momentum would have been precise if this was a plane wave of a constant wavelength spreading from minus infinity to plus infinity. So, for a localized particle, delta x, its position is not known exactly, its momentum is not known exactly, and in fact, you can show that if there is this particle which is located within this amplitude, it is located somewhere here, the spread is delta x, and the corresponding Fourier transform has a spread around k 0, this is a k, and the spread is delta k, then delta k delta x is of the order of 1, and delta k is nothing but delta p over h cross delta x is of the order of 1, or delta p delta x is of the order of h cross. This is another consequence of the particle having a wave nature. If I want to reconcile the two, I cannot give the momentum and the associated position in the same direction with the same precision as I do classically, and their product actually is h cross. This is a statement of uncertainty principle, which we will come back to in later lectures, but right now just I wanted to convey that if you look at the wave and particle nature together, you cannot specify the momentum and position to as much as accuracy as you like. They have a reciprocal relationship, delta p delta x is of the order of h cross. So, now back to this representing this wave packet, which in the previous slide I wrote as a Fourier transform. and I am going to write this psi x as equal to minus infinity to infinity a k e raised to I omega t minus k x d k. You may wonder why I am integrating only over k. It is because omega is also a function of k. Now, let us say at t equal to 0, the profile was given by, let us say, psi 0 x, which is integration minus infinity to infinity a k e raised to I minus I k x dx, and this is psi 0 x. What happens sometimes later? And this k a is peaked around k 0. So, I am going to write now psi x comma t, and you recall from our earlier lectures that when I want to write the time dependence, I will just put in the time dependence as happens for a wave. So, it will be e raised to I omega t minus k x d k. With time, this is how the psi function or the wave function is going to look like. Recall when I did the string and I said if I give it a shape of triangular string and displace it, with time the displacement was given as a sum of all the eigen frequencies and eigen functions. In exactly the same manner, this is what I am going to write. And now, since a k is largest near k equals k 0, we will expand omega k as omega of k 0 plus d omega d k at k 0 delta k. So, I am going to write now psi x t is equal to integration a k e raised to I omega 0, which is corresponding to omega t t, which is corresponding to k 0, minus k 0 x times e raised to I d omega over d k at k 0 delta k minus delta k x d k minus infinity infinity. Since the portion shown in the curly brackets does not depend on k, I can pull this out and write this as e raised to I omega 0 t minus k 0 x integration minus infinity to infinity. Instead of writing a k, I can write this as a function of a delta k, where delta k is difference from k 0, e raised to I d omega over d k at k 0 minus x, there is a t here, sorry there was a t here, delta k and integration over delta k. And what is this? Recall a k e raised to minus I k x d k was this function which was giving the profile of this wave, right. So, this is what I had shown you earlier, that this was that psi 0 x. So, I am going to have the same profile come in, and this is going to be psi 0, except now I am going to have d omega over d k at k 0 t minus x. So, what has happened? This profile that was there in time t, it has shifted by a distance d omega by d k at k 0 times t, and therefore, it is now given as psi 0 of d omega over d k at k 0 t minus x. If it has shifted by this much d omega by d k k 0 t, that means it has moved with a speed v equals d omega by d k at k 0. So, there was this particle which is being given by this profile of wave, and in time t this fellow moves by a distance d omega by dk calculated at k 0 t and moves the same shape. The particle has reached here, and therefore, this implies the speed with which it has moved is d omega by dk at k 0, and this is known as the group velocity. V g is the group velocity, because it is a group of waves that has moved, and this group velocity should be the same as the speed of the particle. And let us check that. So, E is given as p square over 2 m, which by now you are familiar is h cross square over k square over 2 m. So, omega, which is E over h cross, which is same as 2 pi E over h, is h cross k square over 2 m, and therefore, d omega over dk at k 0 is going to be h cross k over m at k 0, which is h cross k 0 over m, which is same as p 0 over m, which is same as the particle velocity. So, we say that the particle velocity or particle speed is the same as a group velocity. So, to conclude, when I associate a wave with a particle, the particle is described by what I call a wave packet. This is a wave packet, and the speed of particle is same as group velocity. In the next lecture, we will develop the wave equation for this wave and start solving problems using the Schrodinger equation.